Hi, my name is Champwikit. Today, in this video, me and my group member, which is Anutik Lelaki Nikom, Hasaratan, Nurul Shahira, and Nurul Arifah Balkis, we will present about the assignment case study, which is investigation the effect of electromagnetic interference due to radiation emission. So, what is radiated emission? Radiated emissions refers to electromagnetic energy emitted from an electronic device or system propagating through space without the use of a physical conductor. These emissions can interfere with other electronic devices or systems if they operate on similar frequencies, leading to potential communication and functionality issues. Regulatory bodies often impose limits on radiated emissions to mitigate interference and ensure electromagnetic compatibility. So now talk about the effect of radiated emission. Interference with electronic equipment. This interference can manifest as errors in data transmissions, malfunctions, or complete failure of affected equipment. Electromagnetic compatibility concerns. In complex environments where multiple devices are operating simultaneously, radiated interference can interfere with the proper functioning of co-located equipment, leading to performance degradation or operational issues. Last one is the security risk. Intentional electromagnetic interference attacks involve generating powerful electromagnetic field to disrupt or damage electronic systems, potentially leading to security breaches or data loss.
Hi, my name is Anutik Nalakinikom. Today I will demonstrate the data from investigation the effect of electromagnetic interference due to radiation emission based on data collection from 1.5 meter, 1 meter, 0.4 meter, and 0.2 meter. So this is a 1.5 meter graph. So this is a water spike. So for the 1.5 meter, we get peak of voltage is 0.925 volt, and the initial we get negative 0.053 volt. So the overall pulse duration is 4 microseconds, and the voltage per division is 0.2 volt, and time per division is 500 nanoseconds, and the rising time 10% to 90% is 1.3 milliseconds. So for this part, my device cannot pin the data tips here. So basically, after I pin the data, this is a collapse on the initial voltage, initial value. So if I move, it's auto same. So this is data from my my teammates. So she get 1.3 milliseconds. So next is 1 meter data. So this is the overall. Overall we get 6.2x microseconds. So for the peak, so for the peak voltage, so this is y-axis is equal to voltage, and the x-axis is equal to times. So if this is for the y value is equal to 2.056 volt for the voltage spike is on the peak. So for the minimum is equal to negative 0.424x volt. So for the overall, so as I said, we get 6.2x microsecond, and the rising time we get 1.09x microsecond. So for the time per division we get 5 microsecond. So for word per division we get we use 0.5 word per division. The figure number 3. So for the 0.5 meter, so for the y-axis for the voltage, and the x-axis equal for the time. So for the word per division, on this part we use 1 word per division, and the peak we get 7.576 watt. For the overall time, so overall for 0.4 is equal to 6.x microsecond, and the crossing time of the highest path, so we get 5.95 nanosecond. So we take from here to here. Here is two data. So first of all, we need to click the data tip first, then we can delete. So we can pinpoint again. Okay, so we get 0 here, 5.95 nanosecond. For the last one, 0.2 meter. So same, x-axis is equal to voltage, and y-axis equal to x-axis equal to times, and y-axis equal to voltage. So for the volt per division, we use 2 volt per division because the highest y value is equal to 15.0x volt. for the voltage spike. So for the overall, we get overall pulse duration, we get 5.4x microsecond, and rising time we get 1.x milliseconds. So this is data from my teammate, and from his device, it can generate the 10% to 90% of peak. So my device is cannot pin the data. So that's all for me. Thank you.
My name is Alifa. I will show the radiated interference result, which is all the data we get from the graph that being conducted by Anuti, and also there are some from me. For this data, there are for distance we use 1.5, 1, 0.4, and 0.2. For the rising time, we get from the time 90% minus by time of 10%. For overall pass, we get it for the wave, the end of the wave, and also the highest amplitude is the peak. And next. Okay, next is radiated interference graph, which is all the graph that being conducted by Anitik. We can saw the peak and also how we get the data, and the details is being shared by Anitik. Thank you.
Okay, hi everyone. For my part, I will discuss about the discussion part. So, for the discussion, unintentional electromagnetic energy leakage from numerous internal sources of electronic device is known as radiated emissions. Understanding the frequency response of these emissions is essential for comprehending their propagation and interaction with other devices. This response is influenced by circuit design, component properties, and environmental conditions. For instance, the radiated emissions produced by automobile ignition coils might cause interference with adjacent electronic equipment. To find possible interference frequency and put mitigating measure in place, engineers analyze the frequency response of these emissions. Understanding the propagation behavior of radiated emissions and optimizing device design for electromagnetic compatibility, which is EMC performance, are made easier by analyzing waveform features and quantifying the highest peak of the emissions. In general, determining EMC and other safety requirements requires examining radiated emissions and their maximum peaks. For example, an ignition coil produces a radiation field emission consisting of many pulses when it generates a spark of voltage. This phenomenon is commonly referred to as a train of pulses. In internal combustion engines, like those in cars, this phenomenon happens during the ignition process. As an illustration, consider what occurs. First one is ignition triggering. The electronic ignition system of the car activates the ignition coil. When the piston of the engine reaches top dead center during the compression stroke, the circumstances required for combustions are met, and this is when it usually happens. Second one is voltage buildup. Using electromagnetic induction, the ignition coil quickly generates a high voltage, frequently in the tens of thousands of volt range. To generate a spark across the spark plug gap, this voltage, which is far higher than the battery voltage, is required. Third one is spark generation. The voltage ionizes the space between the spark plug electrodes when it reaches a critical point, forming a conductive loop. A spark or abrupt release of electrical energy results from this. The fourth one is train of pulses. Rather than being a single, continuous event, the spark generated is a sequence of pulses. A discharge of electrical energy across the spark plug gap is represented by each pulse. Thank you so much.
In conclusion, the model aims to minimize this emission through the fundamental design techniques. Radiated emissions originated from current flow on interconnection and cables, creating changing magnetic and electric field that form radio wave. Experimental equipment includes a picoscope, coaxial cable, flat plate antenna, and a 37.2 kilovolt spark voltage source. The procedure involves spark voltage measurement using a voltage divider and conducting radiated emission experiments with specific oscilloscope setting. The data analysis includes selecting the highest peak from the recorded samples and measuring parameters, concluding with a concise summary based on the finding. Thank you.